Good morning, everyone. Today's lecture is about drillstring design. We'll look at some of the properties that we have to care during the drillstring design, and then we'll do some calculations for drillstring design. Let's start first again. What is drillstring? Our first question is what is drillstring? Drillstring is a section of pipe which consists of drill pipes, drill pipes, drill collars. Uh, you can say some stabilizer, reamers, and centralizers and subs and Indian bit. So it consists of these different parts and it connects the Kelly to the bit. And if I draw the picture, it will look like this one. So this section of pipe is called the drill string. So I can connect this directly. And it consists of these drill pipe, drill collar, drill stabilizer, reamer, centralizer, subs, and bit. Now we are designing the drill string. In order to design the drill string, we have to care for some of the properties. First of them is the tensile strength. Let's look at the tensile strength and how does it looks. I mean, what is tensile test?
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece.
Imagine this is our drill string, the long drill string we are talking about, and see how they are testing its tensile strength.
It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force.
So what they will do, they will try to pull it from both sides and see at what point, at what force this pipe deforms or changes its shapes or become thinner at certain points.
That the test piece opposes
So
to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in the force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material...
They are now giving it a force to extend it from top or the bottom, both sides. And this is the force they are showing, they are applying the force. They keep increasing unless you will see that it will break.
Behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Ludus effect. After a certain strain, known as the Ludus strain, the force increases again. The material opposes an increasing force against the imposed elongation. Its strain hardens, but keeps a cylindrical shape. This means
and now
that
they
the
are
test piece
extending it.
gets longer and thinner, but keeps a cylindrical shape.
So now it is getting longer and thinner, but still the shape is correct. We are looking at the point where the shape deforms or it breaks. This is the tensile strength. Okay, we are extending it, still it is fine.
As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there.
Here it is. So tensile strength is the maximum force where it starts to deform at this point. It breaks. So that's the tensile strength. The strength of the pipe at at what tension it will break. Because as you know, we are dealing with the long distance pipeline or long distance drill pipes or drill strings, which is, let's say, from 1000 feet to 10,000 feet, and most of the pipe is in tension. Because of that tension, there is a tensile forces acting on this pipe in the hole, and we have to make sure that the pipe we are using, it should take care of this tensile. It should not break like this because of the force applied, or because of the drill collars applied. So we have to be careful for that.
In the recorded force elongation diagram as the map Rn, please note
Look at
that
this
the
one.
percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. And shows the elastic behavior. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there.
Look at this one.
As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material.
Now I will stop it here and go back to the slide. Okay. We said that we have minimum yield stress. So this is the minimum yield stress we are talking about, a minimum tensile stress. So these values corresponds to that breakage of pipe under high pressure. And we have to find out this tensile stress, and what is the tensile stress based on the pressure there in the pipes. Now I will show you some more properties that we care.
talking about Young's modulus. These are some of the key words that we're going to be looking at during this topic. So extension, compressive, Hooke's law, tensile, strain energy, spring constant, brittle materials, strain, elastic limit, plastic deformation, elastic deformation, stress, the ultimate tensile stress, springs, ductile materials, load, deformation, and force extension graphs. And not forgetting polymeric materials. So let's begin. Material scientists need a method to predict how materials will extend when given the force, cross-sectional area, and the original length of a material. Now, Young's modulus is a value that assigns a particular property, or you could think of the stiffness of a material. It's a value that's always the same for a particular material, no matter what the dimensions of the sample being tested. And it can be used to predict the extension or compression of an object. So how do you calculate it? Now, before we work out how to calculate Young's modulus, we need to know some definitions. Now, firstly, stress. Stress is defined as the force per unit area of a material. And it can be calculated by taking stress equals force over area. The units of stress are newtons per meter squared or pascals, which is exactly the same as pressure. The symbol for stress is sigma here, and that's equal to the force divided by the area. Another definition that you need to be aware of is strain, and strain is defined as the extension per unit length. So this is the equation to calculate strain, is the extension of the material divided by the original length. So here we've got the original length of our material. Now, if we put it under some kind of tensile stress, it's going to extend by a small amount, E, and that's the extension. Because both extension and original length are measured in meters, strain has no units. So here we have strain is extension divided by length. And finally, our final definition is Young's modulus is defined as the stress per strain. So to calculate the Young's modulus, you just divide a value of stress divided by a value of the strain. And normally Young's modulus is given the symbol E. We've got sigma from before, which is our stress, and our strain has got the symbol epsilon. So you can think of Young's modulus as being a measure of the stiffness of an elastic material. And now I'm going to invite area. Subscribe.
Okay, now I will go back to this previous video and talk about it. So Young's modulus is defined the stress over the strain. Stress is, in this example, stress is the force that is applied to make it longer. Okay, this is a stress. And what is a strain? The change in the length. This was the, here was the, this is the original length of the pipe. And if you look at it here, it is extended. So this is the change in the length. I mean, it's longer than here. And what is the?
The screen is not shared.
It's not here? Okay. Here, look at this one. Here you see it breaks. So now there are two things important in this one. One of them is the force applied, which we are applying to make it longer. That is called the stress. The force applied that can make it longer. That is the stress. And what is the strain? Strain is, as we saw in the previous video, is a change in the length. For example, this is the original length from here to here. This is the original length. But when you change it to here, just you minus both of them is a strain. A strain is the change in the length of the pipe. So and what is Young modulus? It is the stress over strain. I mean, how much force is applied and how much was the deformation. So actually, overall, you can summarize this. It's the stiffness of the material. So at what force, how much it can deform. And this is important because we are dealing with the long distance drill strings, a very long drill strings, which has a lot of weight and forces acting on them. So we take care of tensile. Otherwise, our pipe can break and so on. And here it is. So we are applying a stress on it. Okay, this stress is making it longer up to the point it will break. This is the tensile stress. So we don't want such situation in the drill string pipelines and so on. Okay, then there's one more last one before we go to the our calculations.
It's originally 8.5 centimeters. However, when we add the tension before it breaks, it is 19.5 centimeters. But the hairband didn't go over its elastic limit because it can go back to its original.
So the elastic limit or elasticity is the maximum you can stretch it.
Our second example is a spring. The spring was originally 2 centimeters long, but as you see, it went over its elastic limit, so we will not be able to demonstrate it. We can reach until 6 centimeters when we stretch. The last example is a cloth. It is about 26 centimeters when we don't add the tension. But when we pull it, it is 30 centimeters. And as you can see, it went over its elastic limit. As we saw examples, when an object goes over its elastic limit, it won't go back to its original shape.
Yeah, so when the elastic limit is achieved, it will not go back to the original shape.
The second to show you is Hooke's law. Hooke's law says when we double the force extension of the width. If we make the graph based on it, we will get the linear graph like this. First example of Hooke's law is measuring shoes. When you put only one shoe on the Newton meter, it is about 400 grams. It should be 800 grams when we put another one according to Hooke's law. So when we check it, it's 800 grams. And this is matching to Hooke's law. Our next example is measuring chalkboard erasers. If we put only one eraser on the Newton meter, it is 200 grams.
Okay, now we start some calculations and we see how this goes. There it is. Okay, let's look at the first question, what it is saying before we go for the designing. What is the weight in air of a joint 30 feet of 5-inch? Okay, so diameter, outer diameter is 5-inch. The weight of the drill pipe is 19.5 pounds per feet. Grade is G. Drill pipe with 4.5 IF connections. Okay, what is the wet weight of this joint of drill pipe and immersed in a drilling fluid with a density of 12 ppg? Now, let me first go back to the whiteboard again and explain some concepts. This is the pipe which is outside of the drill fluid. Now, when we talk about this pipe, okay, this is the pipe. The total length of this pipe is 30 feet. Okay, where we want to calculate weight of the pipe with joints in open air. I mean outside when it is on the land somewhere. Then this same pipe we are going to put inside the hole where which is full of drilling mud. Okay, now we have this borehole here. It has drill pipe 30 feet long, and the drilling fluid has density of 12 ppg pounds per gallon. Okay, now this pipe we will put it uh, here inside this one. Okay, now we have to find out what is the weight here. What is the weight at this point inside the pipe? Weight of drill pipe inside the borehole. Now my question to all of you, will it be the same or different? If different, why? If same, why? Anyone has any answer?
I think it would be different because there would be more fluid or pressure in down the further you go down.
Yes, it will be different. Anyone else?
I believe it is different because the pressure of air is totally different from the pressure of the earth, or we can see water or any material that we have in the earth.
Yes, I agree. Anyone else?
It would weight less due to the buoyancy provided by the drilling fluid.
Exactly, buoyancy force of the drilling fluid. It will make it less in weight. So first we have to calculate the buoyancy force, and buoyancy force depends upon the mud density. So first we calculate the buoyancy force or mud weight based on the mud weight that we have, and then we see how much is the buoyancy force. We multiply with the overall weight, we get the new weight. So let's look at the question and how it is aerated. This is what he is asking: weight in air outside and weight inside the borehole. Okay, when it is immersed in a density of 12 ppg. So here it is. Well, as I said that, let's look at it. Our joint is 30 feet. Okay, and what we are looking at 5-inch 19.5 pound per feet grade G. Now, when we talk about the grade G and 4 half connection, IF connection, we have to look at its weight also. Okay, so what we will do, we have in drilling engineering, we have lots of tables, and these tables tell us about the details of the weight and based on that. So let's look at this table. I hope you can see that. We are looking at the 5-inch pipe, and the tool joints, we are looking at 4.5 IF. The weight, there are two different weights, but the one in our example is 19.5. And the second thing which we are looking for is a G grade pipe. Okay, when we have the G grade pipe, 19.5 nominal weight, the overall weight per feet is 21.5. Here, this 21.5. So this 21.5, we go back, we apply here 20, and the total length of the pipe is 30 feet, so it becomes 645 pounds. Got the idea what I'm trying to say?
Sir, can you repeat it again, please?
Yeah, sure. Now, what we want to do, we want to calculate the weight of the drill pipe inside in the air. Now, when I say that we have a drill pipe, this one, we have to look at the weight 19.5, which we are talking about. 19.5 pound per feet. We are talking about the weight of this section. It starts from here and ends till here. This is what we are talking about. Now, when we do the calculation of overall weight of this pipe, which is this all pipe, we have to adjust the weight of tool joints also. Now, in order to adjust the weight of tool joint, we must know what is the type of the tool joint we are using here at this point. What is which kind of tool joint we have? Here we have 4.5 inch, 4.5 inch IF connection. So we have a long list of tables with different pipe sections and different tool joints. We have the nominal weight, and based on that chart, we find out the weight of all this drill pipe per feet. This is what we are doing. So now let's go back and look at the, here it is. This is the table we have. We said that we have a pipe here, which is 5 inch. So we will go here, find the 5 inch. Where is the 5 inch? Here is the 5 inch. Now we said that the connection joint here is 4.5 IF connection. So here is the 4.5 IF connection. So we are looking at this section. We are concerned with this section, not the other section, because they are talking about the smaller pipe, 2.5, 3, 2, 3 by 4, 2, 3 by 8, and so on, and so on. Now, other thing mentioned here is the weight of the pipe, which is 19. This is the nominal weight, not the weight without the tool joints. So this is the weight, nominal weight we are talking about, 19.5. Then we are looking at the grade, what kind of quality we are using, because we have 4 different grades based on their tensile stress. The tensile stress, as you saw in the video, I showed you that it can break the pipe. So we have 4 different qualities of pipe we are using in Drillstring design. So here is a G grade pipe, G105, and we are looking at its weight per feet. So its weight per feet is 21.5 pound based on the grade, based on the nominal weight, based on the connection. So there are 3 things important here. If I make the, this is what we are looking for. Yeah. Okay. If I can use the brush here. There is no way to put the picture here. So I have to use the other format. Okay.
So you can use snapping shoot if you.
I can use paint maybe. Okay, here's the pipe, and what we are talking about is this section. Okay, based on the 5 inch outer diameter of the pipe, as I said, the weight, that 19.5 we are talking about here, is without the tool joints. We have to consider the weight of the tool joints also. So weight of the tool joint is basically first we have to look at what kind of connections we have. We have different kind of connections. See here we have NC26, we have NC31, we have NC38, but the one in our question is NC50 or and 4.5 in connection, IF connection, this one. So we have this connection based on this 19.5. And the third thing mentioned is the yield stress of the pipe that can handle that. We are talking about here G grade pipe. So when you connect the dots and all of these points, this 5 leading to this 19.5, leading to G5, we get this weight, 21.5. And this similar thing, we just go and multiply it by 30, we get the weight of the we get the weight of the drill pipe, which is 645 pounds. So 21.5, the total length of the pipe is 30 feet. So we just multiply, we got 645. I think it's clear now.
Yes, yes, sir. Thank you.
Okay. Now the second part of the exam, this question is that what if this weight, this pipe is immersed, I mean, is dipped or immersed in the density of 12 ppg. We have a drilling fluid inside the borehole with 12 ppg mud. How much will be the weight? So in order to check and calculate the weight of this drill pipe, which we calculated 645, inside this drilling fluid, we must consider the buoyancy factor. So buoyancy factor we have to calculate by, it must be calculated based on the mud weight. Mud weight is given here, which is 12. Formula of the buoyancy factor is given. You divide 12 over 65.5, 1 minus that, and you get the buoyancy factor 0.87. You simply multiply this one with the other one. Now, there's an important observation that we can look at it. Okay. Here it is. Now, if you look at the observation here, the weight in air was 645 and weight inside the drilling fluid is 527. So weight is reduced now. And this is one of the function of drilling fluid to support, one of the function of drilling fluid is to support the weight of the drill string. So function of drilling fluid is to support the weight of the drill string. And it happens through the buoyancy factor. And buoyancy factor, which we found out using the formula, we see that the weight reduced from 645 to 527. This is the first question that we just saw. Now let's go ahead and make some more concepts about it. We use this table, and if in an exam this question comes, this table will be given. Now we are looking this. The first question was for the drill pipe. Now the similar kind of question we are looking for the drill collar. As you know, drill pipe and drill collars are different. The function of the drill pipe is to provide the length up to the drill string. Function of the drill collar is to provide mainly the weight over it. So the weight of drill collar is much more than the drill pipe. And you will see that here in this one. Now first, let's look at what is the weight in air of 200 feet pipe. The outside diameter is 9.5 inch and the inside diameter is 213 by 16. Okay, which is quite low, 13 point. So look at the wall thickness here now. So we have a 200 feet of drill collars. The outside diameter is 9.5. Inside diameter is 213 by 16. What is the weight in here? So based on the dimensions, outside diameter and inside diameter, again, we have to go through the tables and find out the weight based on this one. So we have a table here. This is the outside diameter. And here is the one drill collar weight. And again, I have to go back in the painting. Okay, here it is. Now we are looking at the pipe which has 9.5 inch one. And we have to find the weight of the drill collar based on the outside diameter and the inside diameter. So this first one represents the outside diameter. Now let's look at it, what this outside diameter is doing. So we have a drill collar which is outside diameter 9.5. And we proceed till the inside diameter is coming up. The inside diameter for us is 213 by 8. So the pipe which we are dealing with, its outside diameter is 9.5 and the inside diameter is 213 by 18. So when we have outside and inside diameters are given, based on this table, we can find out the weight of the drill collar, which is 220.4 pounds per feet. So we just put this value back with multiplied by 200 and we get it. Got the idea? Any question? Is it clear? Okay.
Yes, sir. Thank you.
Yeah, just I want to repeat it. We are here trying to know the drill collar weight, weight of the drill collar per feet. In order to find the weight of the drill collar per feet, we must know what is the outside diameter and what is the inside diameter. A question is given to us. It is mentioning the outside diameter, which is 9.5, 9.5. Its inside diameter is also given 12, 13 by 18. We just find out based on that, we went to this chart towards the borehole at the inside diameter and found out our weight per feet, which is 220.4 pounds per feet. The same value now we will go back to the example uh, here, and we will just multiply this 220, and we want to know at 200 feet. So we just multiply, and you see now for 200 feet, how much is the weight? 44,080 pounds. This is the weight of the drill collar. And as I said, the function of the drill collar is to provide the weight to the drill string, and drill pipe provides the length. So weight of the drill pipe is not too much as compared to the drill collar. So here is the weight of drill collar with respect to 200 feet of pipe. Yeah. Now the same thing is we have to look at it. Okay, this is an air. What is its weight in the borehole where there is a drilling fluid? And in the question, it is mentioned that the mud weight of the drilling fluid is 13 ppg. So 13 ppg, 13 ppg, we calculate based on this formula again, which is mud weight over 65.5. Using this formula, we find out the buoyancy factor here is 0.801. So the original weight in air outside, the weight was 44,000 pounds, but because of the drilling fluid is supporting the weight, now the weight becomes 35,308 pounds. This is the one. Okay. Now, the third question, is it clear till here? Any questions? Yes. Okay, thank you. Now, let's go to the third one. It is not uncommon for 5-inch 19.5 pound per feet drill pipe to be used in the same string as 8 1/4 and 213 by 16 collar. So what we are trying to do, we will connect, we have to make a drill string, and drill string is you can say that it's a use of some of the drill pipes as well as some drill collars and some other equipment. It's a complete package of drill collar, drill pipe, and some others. We use 19.5 pound per feet drill pipe, 5-inch outside diameter with the 8 by 1/4 to 213 by 16 drill collar. Means outside diameter of the drill collar is 8.25, and the outside diameter of the drill pipe is 5-inch. If I depict this one in the one, so it will look like this one, drill string. Outside diameter of this drill pipe, this is drill pipe, and this is drill collar. Okay. Outside diameter is 5-inch, and outside diameter of this one is 8.25 inch. And you can see here the difference at this point, because the diameter above pipe is 5-inch, inside one is the outside diameter. I'm not talking about inside diameter. So the question 3 says that you must compare both of them, their inside and outside diameter. Compare the nominal ID, inside diameter of drill pipe and drill collar. Now, first, again, we have to use the table. First of all, for the drill collar, the inside diameter is already given, which is 213 by 16. So inside diameter is 213 by 16 inch, is already given. Okay, 213 by 16 inch is already given. But for the drill pipe, again, we have to go through the table and to find the inside diameter of the drill pipe. So for that, we have this table here. So we have, again, we will use the table, 5-inch pipe. The weight is given 19.5. So we have 3 different kinds of 5-inch pipes, which is talking about 19.5. So 5-inch outside diameter, weight is, nominal weight is 19.5. Its inside diameter should be 4.276. The same thing, we will just go and put it here, 4.276. from the pipe. So now you can compare that the drill pipe has a higher inside diameter and drill collar has a smaller drill diameter. So it means that there will be a restriction inside the drill string for the drilling fluid to flow. And there will be some change in diameter, and diameter change will definitely change the pressures and so on inside the pipe. That we have to consider that. Any question? Or I should repeat? Okay. Now we have to calculate the weight of the bit, the length of drill collars for the given weight on bit. Okay. Let's look at this question again. You have been advised that the highest rate of penetration for a particular 12 1/4 bit, so the outside diameter of the bit is 12.25 inches, will be achieved when 25,000 pounds weight on bit is applied to the bit. We have to apply the weight on the bit. Total weight is 25,000 pounds. We have to apply the weight on the bit. Okay, 20. But how many drill collars we need in order to apply that one? Assuming that the bill will be run around 12 ppg mud, the drilling fluid that will circulate. We are mentioning here drilling fluid because, as you know, there's a buoyancy factor. Buoyancy factor will reduce its weight, so we must mention the drilling fluid material, the density, mud weight density here, which is 12 ppg. We need to calculate the length of drill collars required to provide 25,000 pounds of weight on it. We have to calculate how many drill collars we need to use. One. There is one thing. Then we have three things that we have to calculate here. Calculate the weight in air of 10,000 feet. So now we are drilling a well which is 10,000 feet. The pipe we are going to use is 5-inch 19.5 G grade drill pipe with 4.5 connection. That you saw in the previous example. We are going to use that one. But in that question, we calculate just for 30 feet. Now we do the similar calculation, but we have to find out for 10,000 feet. Because the well we are drilling is total 10,000 feet. The second thing is we have to calculate of this string in 12 ppg mud. So we have a 12 ppg mud in all the borehole of this 10,000 feet, and we check how much is the weight in air and how much is the weight inside the well. Then we have to calculate the length of drill collars, 9.5 to 2. How many drill collars we should use when we have to provide 25,000 weight on bait and keep the drill pipe in tension and 12 ppg. Do you understand the question, or should I clear it more? So there are three parts of this question. First part is asking for drill pipe. Second part is also asking for drill pipe weight. Third one is asking for the drill collar weight inside the drill string, inside the borehole. Let's look at it. We will follow the same procedure. We have to find the weight in air. Again, we have to go back to the table based on this 19.5 pound per feet grade G with this connection. We find out the total weight per feet of the drill pipe, the total weight of the drill pipe, which is 21.5 pound per feet from the table. And we use this table for that, this one. And here is the 21.5 based on 19.55 and this one. After that, this one, you multiply by 10,000. So total weight of the drill pipes in the hole outside in the air will be 215,000 pounds. As we discussed earlier, the buoyancy factors plays a major role in this in the weight of the drill string inside the drilling, immersed in the drilling fluid. So we have to consider the buoyancy factor. For calculating the buoyancy factor, mud weight is given, which is 12 ppg, and we just multiply this buoyancy factor with 215,000. We find out that weight of the drill string of 10,000 feet, 5-inch drill or outside diameter, 19.5 pound per feet nominal weight, grade G pipe will have total weight of 175,655 pounds. This is the weight in air. Now, based on that, we go and find out how much is the weight drill collars are needed to provide the weight on bit, which is only 225,000 in 12 ppg mud. Okay. We are talking about the weight of the drill collar, which is 25,000 pounds that it has to find out. Now, in order to find out, first of all, we need to know that how many feet of drill collars are needed. How many drill collars are needed? So for that, based on this 9.5 and 213 by 16 drill collar, first we have to go and find the weight of this one drill collar. Okay, so we use this table here, which is 9.5 and 213 by 816 or 18. The weight of the drill collar is 1220.4. The total weight is needed 25,000, and 220.4 is the per feet weight. We multiply buoyancy factor. We find out that how much is the total length of drill collar is needed. Here is the length of drill collar which we need. Okay. Now, so we need 139 feet of drill collars in the drill string. Our drill string is 10,000 feet, but out of those 10,000, 139 feet should be drill collar. Based on, because total weight of drill collar is nearly 25,000, we divide it by per feet weight and multiply by the buoyancy factor, because the weight in the drilling fluid will be lower than the outside air. So we have to consider the buoyancy factor. So here it is, the buoyancy factor 139. Now, in order to have the safety, ensure the drill pipe is in tension while drilling, we have to have some safety factor for that. And how much is we need some additional length of collars will be required to overcome the buoyant forces of the drill pipe, and from above will be equal to 1. So in order to consider the additional section of drill pipe that we need 250,000, 15,000 of drill pipe. This is the in open air. This is one is in the you can say in the inside the borehole with the drilling fluids. So we just minus both of them, divided by 20 point, which is the weight of the drill pipe, apply the buoyancy factor. So we need total 219 feet of drill collar more in order to keep the drill pipes in tension and to provide the weight on bit in compression. We need 219 feet of drill pipe more. And definitely we just multiply the safety factor with 15%. So we add 139 feet with 1.15 safety factor, add this additional safety, which is 290 feet. The total 379 feet of drill collars are needed in a 10,000 string in order to provide the weight of 25,000 feet and to keep it in compression and to keep drill pipes in the tension. Okay. You got the idea, or I repeat?
So can you repeat that second part?
Okay.
219 foot.
Yeah. Okay. Now let's start from the question. What question is asking? Question is asking that we need what would be required to provide 25,000 pounds weight on bit in 12 ppg. So we have to find the length of drill collars needed. The first thing we did is we find the per feet weight. We have to find the weight per feet. How much is the weight per feet of this drill collar? We went back to the tables given to us. Based on the table, we find out the weight per feet of the drill collar is 220.5.4. Total weight is a logical thing that total weight is 25,000. We divide it by 22. We find out how much is the total length of the drill collar is needed at this point. So 25,000 is the weight on bit that we need to apply. 220.4 pound per feet is weight of drill collar per feet. This is the buoyancy factor because weight inside the drill borehole is lower than the outside diameter. So that's why it is 139 feet. Now we said that in the drill string, the upper part, drill pipe, has to be in tension and the lower part provide compression. And there is a neutral point. So in order to keep the pipe in tension above one and lower in compression, we need some extra drill collars that can perform this job. How much is the need to keep the extra drill collars? We find out by first finding the difference of the buoyancy forces on the drill pipes. So we have total, because now we are dealing here with the tension and compression of the drill string. Upper part has to be in tension, the lower part has to be in compression. In order to achieve that function, we need an additional length of drill collars so that the above should stay in tension and lower part should stay in compression. So what we did, we minus the weight of drill pipe in open air from the inside immersed in the drilling fluid. We already calculated 215 and 175. This one here. This is the weight of drill collar. We apply the buoyancy factor. So total 219 feet of pipe is needed in order to keep the drill string in tension. If I show you tension and compression, here it is, one diagram. So we have the lower part are the drill collars, the upper part are the drill pipe. The upper part drill pipe section has to be in tension and tensile stress is acting on it. The lower part has to be in compression. So this part provides a force downwards and this part is in always in tension, supports the weight of the drill collar, and so on. So that's the function. In order to achieve this function, we have to have some additional weight of the drill pipes and drill collars. So for that, we just multiply the open in air drill pipe minus the one which is the inside the drilling fluid. We multiplies by 20, divide by 120.4, which is the weight of the drill collar, and buoyancy factor, which is 219 feet. In the end, we just add them and multiply as 1.15 safety factor, and that's the total length of drill collars we need. So the question answer for this one is we need 379 feet of drill collar needed in order to to have the weight on bit 25,000 pounds and so on. So any question from here? We will stop it here and we will continue the this tension design procedure in the next one. This one we will continue in the next one because we cannot finish it here. It needs our lecture to understand this one. Is any question till now?
Doctor, I have a comment about our presentation.
Yes.
As you know, you have provided us some topics,
Yes.
but as you know also, we have more than 5 classes.
Yes.
And we cannot study on all of them.
Well, no, you have to study. And I say, as I say, this is just the presentation. You will see more things. Projects I'm putting on project today. Then I'm putting, so there are a lot of stuff coming.
Yeah.
So you have to manage your time, learn time management.
Yes.
Okay.
And
so,
about this formula, Doctor, if we have a homework, weekly homework, we can more experience those formula for the final exam or the midterm exam. I believe it's the better way to more study on them.
Yes, you can do that. It's no problem. I mean, you are now graduating engineer. What homework? You are an engineer. You should know if you think you need it, you should do it. That's it.
Yes. Thank you, Doctor.
Yeah. Right now, for me, you are an engineer. You are not a student. I give you homework.
Yes, that's right. But as you know, because we have more classes, that's a problem for us.
It's not a problem. You manage your time. Take it as a challenge. Manage your time.
Yeah.
I think I'm more busier than you. I think so.
Yes, that's right.
Yeah. And
Thank
everyone.
you,
yeah. So just manage your time. Just learn how to manage it. And this is the way to solve your be positive and try to see how can you achieve your target. And as I tell you, this is just the beginning of the course. First month we were just trying to make some concept. Now we will do some projects, some presentations, some tests, some midterm. So there's a lot more coming. An advanced level.
Yes, that's
okay.
right.
All my courses. Yeah. And for example, I have 3 courses. I'm not sure how many you are taking, but all of them will follow the same track. So these 3 courses will make you very busy. Okay. And
sir, are you gonna replace the test with?
No, because university I think said after 15 October we can do the test on campus.
No,
sir.
They said they tried.
We just got emails from.
Yes, university said that to me in an email that after 15 October you can place your assessment tools on campus.
Sir, we got email from Mr. Wolfgang. He mentioned that only final exam will be considered on campus. All the other stuff will be online.
Only?
Yeah.
Sorry, your voice is cutting. Can you write on chat box?
Sir, the Dr. Wolfgang, he said we only might do the final exam, so it's not sure.
Okay, when it was?
Sorry?
When this email was?
He said he'll do some like trial experiment with a class to see if it works going back to campus, but he'll do that in November. So
okay.
Yeah.
If that is the case, we will see. We will follow the situation.
Okay.
We will follow. My concern is less on the assessment, more on the transfer of knowledge to you. Okay, grades in the end we will do it somehow. But the question is that the online experience is different than the on-campus. Being face-to-face class is different than the online one. So the overall idea and objective is how we can transfer the knowledge to you and you get maximum benefit of the class and get some idea about the subject. That's the main objective. And so far, I think we are doing fine with the subjects because the presentations are a good way to get the feedback of the students and the
So
project.
I think we can also do like quizzes, like these questions, the calculations. We could do it as quizzes for
We
so
can do
basically
that.
an assessment for the grades.
Yeah, we can do that.
Yeah.
We can do that. For example, I give you, let's say, next 1 hour, or let's say tomorrow, 12 to 1, there will be exam. Okay, and I can give you some of the examples to solve. So if I give you only 1 hour, so probably there will be very less chance for students to go and ask others or solve it.
And so you can like watch us on Zoom. So
Yes. Well, this one, some people like to open the camera, some people do not like it. So this is a bit critical here. If you ask, for example, in my previous semester, it was male student, not even a female, and he said, "Sir, it's Ramadan. I don't like to open my camera. So what can I?" Well, I mean, this kind of a answer. What can you do? So I really, after that, I don't ask anything, and it was an exam, right, for presentation or something. So on camera doing is a bit harder here.
as you said, it's about the transfer of knowledge. So
Yeah.
if we cheat, then we don't learn anything.
So that's the point. You should there's ethical responsibility, everyone. But in Kurdistan, I think it's not going to work like this. there is a different way here. This is my experience. Presentation is better. At least the other person is speaking. There is some presentation works.
So sometimes like I'm not very good at public speaking. Like if it's live, then like my throat dries and sometimes I can't speak.
Yeah. That's the fear we have to finish. I mean, that's what we are here for. But what can we do is we can float some projects and with deadlines.
The
So
project idea is good as well.
yeah, project can work, and project is going to help you also in the future. And tests are good, but let me find some way out, because I want to find a website. When you open that, it should not allow any other uh, Google or thing to open. Okay, so in that case we can do exam. For example, I give a questions in that application or website, and then it does not let to open any other thing to cheat,
Yes.
something like that. So let's see, I'm still
Sir,
confused.
why,
Yes,
sir, why don't you replace the exam with the project? Isn't that better?
yes, we will do that. We will do that. Let me post the first project and see the feedback of the students of the project. Today I will post one project, and I will provide you the software for that also. It's about the drill string and making drill string and casing and all that. So today we do that. Let's see how it goes. But please be ready that you are just upset with the presentation that you have no time. Actually, there's a lot of work coming for you, a lot more. So don't give me excuse of time, because you have to do a lot. Just manage your time. Every day you will have something. You take it like this. Every day you will have something to do. Then so manage your time. If you have taken the courses, you should be able to manage it also. It will go fine. In the end, we will do something which is doable. We will not go something which is not beyond the boundaries of our capacity or within 24 hours limit of a day. And I will consider that whenever I see that some student need help and he has no time, then I will extend the time for them. Okay. Okay, then see you in the next class.
So the presentation is on Tuesday, not